Welcome to Brain Vision.
In this question, the first part, we want to find the velocity of the stone, right, when it reaches point B. So basically, it's converting this gravitational potential energy into kinetic energy. So total kinetic energy at B must be equals to its initial kinetic energy plus the converted GPE, which is just mgh. Right, so the initial kinetic energy we are given is it starts off with 10 meter per second, right? So we just take 15 kg, just 10. The total converted gravitational potential energy is taking mgh, where h is the height, right, from between A and B, and it's given to be about 20 meters. Right. So next we just have to evaluate this using our calculator. This is 3698 joules. Now we equate this to half mv square, where v, this is the final velocity at B. So v must be equals to 3698 times 2 divided by the mass. Then we take the square root of this. We should get 22.2 meters per second. Now to get what is the distance that this spring will be compressed, we're going to assume it's compressed by a distance of x, right? Some unknown x. And we know that x plus 100 meters, this will be the total distance that is traveled by our stone. The total distance can be used to calculate what is the work done by the friction. We just take the frictional force multiplied by x plus 100. This will give us the work done by friction. So why do we want to find work done by friction? Because the work done by friction plus the elastic potential energy that is gained by our spring must be equals to the total kinetic energy that the stone must have at B. So at B, we already found that this is the total kinetic energy, which is 3698 joules. So we just want to add elastic potential energy, which is half kx square. Now the problem is, how do we know what is the frictional force? Right, that's quite simple. We just take the coefficient of kinetic friction multiplied by the normal force that is exerted on the rock, which is dependent on the mass, right? Or that the rock is exerting on the ground. Right? So this is just mg. We are given that the kinetic friction coefficient is 0.2. So the overall equation is, sorry, substitute the value in, it will be 0.2 times 15 kg times 9.81 times x plus 100 plus half. The spring constant is given to be 2 Newton per meter. And this is our quadratic equation. What we need to do now is just to rearrange this a bit in terms of just the from highest power of x to the lowest power of x. So x squared, we expand out this bracket and we keep only the x term, should be 29.4x, and then we bring 3698 to the left hand side. It's negative 750. We solve for this quadratic equation, and the positive root of this is 16.4 meters, and we just throw away the negative answer because x, the distance cannot be negative. So this is the extension, the compression of the spring. Now to determine whether the spring will move, the rock will move after it has come to a stop, we need to consider what is the force that the spring is exerting on the rock. So the force exerted by this spring on the rock is given as kx. Right, so we take 16.4 times 2 Newton per meter. So the spring will exert 32.8 newtons of force on our rock. Consider the static friction. So the maximum static friction, we take the coefficient of static friction multiplied by mg. This is given as 0.8. We should get 1.8 newtons, which is greater than the force of the spring. And so this tells us that the force of the spring is not strong enough to push our stone to start moving. Right, and so the stone will remain at rest after it compresses the spring.